G'day, and welcome to the Snowies. Beginning today at Mt Townsend and having a look at the glacial features in this area. And initially, off to the northeast, this area is likely the place that Russell Tarn used to exist. Russell Tarn was noted and named by Richard Helms in the late 1800s and was also known as Lake Clare. Judging from the indentation, the tarn would have been about here. Rocks on the left appear to be part of the moraine wall that dammed the tarn. The water was reputedly warmer than any of the freezing springs that issue from this area. The tarn drained in the early 1900s. That's the problem when ponds are dammed by moraine. The watercourse can eventually work its way through. The Mt Townsend tooth up there. See that thing from miles away. And Mt Townsend itself is probably classed as a nunatak, which is when the ice goes around an outcrop and it's poking out. And it's one of the mysteries of these mountains that Mount Kosciuszko is 20 metres higher, but it has a rounded summit. In alpine regions, a rounded summit is often an indication that an ice sheet ground across the top of a mountain. It remains to be explained why Mount Townsend's rocky summit didn't receive the same treatment. In this view from Mount Twynham, we can see the two summits on the skyline. Mount Kosciuszko being rounded and smooth, while Mount Townsend has a sharper profile. Let's just come around to the south side of the peak now, which is always a good side for glacial stuff, the south side being the coldest side. Smooth vertical walls like this can be formed by ice moving sideways across them. Often scratching occurs, giving some indication of the direction of travel of the ice. But any scratching from the last glacial period has apparently worn away by now. That was over 10,000 years ago. But snow will also move rocks, and that can cause scratching as well. This one's probably done by a snowbank that's thawing, and they shift downhill. The rocks become frozen into the bottom of the snow. While scratches wear away fairly quickly, deeper grooves last longer, as in these rocks by the trackside. These crescent-shaped gouges are another long-lasting example of glacial abrasion. And there's a lot of accumulation in this valley. It's possible that a small residual glacier persisted in this spot as the warmer interglacial period developed. That would make this the end moraine, marking the final extent of glacial ice in recent times. The ice would have lasted here because these southern slopes are more sheltered from the heat of the sun. And that hill on the right is likely to be a line of moraine. This moraine seems separate from the rocks below, and that would be because glacial features in a given area are usually a mixture of formations created over different periods of time. And a little lower, you can see it's a real accumulation point. It would be safe to assume that this ring of rocks is a more recent formation, as the rocks would have been carried away by any larger body of ice that formed later. More smooth faces and terracing. Snow and ice must accumulate to a depth of 45 metres to form a moving body of ice. When we see extensive polished surfaces high in a catchment like this, they've often been created in an extra cold period. When the rocks are mixed up in different sizes like this, pretty sure it's called unsorted till. water action sorts the till over time. The smaller ones move downstream quicker than the larger ones. The finer particles of grit and dust move ahead and settle in the lowest places such as lake beds and floodplains. In this case, a small plain has formed beyond the rocks where a swamp has developed in the boggy ground. And from this basin we can see up onto the head wall where all these rocks have come from. As just mentioned, these southern faces remain shaded and cold, protecting the ice from the heat of the sun. I think this is caused by having a high amount of mica in the granite. Granite is formed as an underground lava, and distributions of the minerals can vary in the hot magma. And this is the line of moraine. I'll climb up onto it. And here we see to the Abbott range. The area below seems likely to be another source of glacial ice, which would have flowed along both ends of this valley. Along the line of the valley to the southeast, colder conditions would help the ice to grow larger and last longer. Consequently, this valley has been ground into the classic U shape as the ice has travelled along it. Ice flowing off the western end of the valley would be subject to the heat of the afternoon sun, which results in a higher rate of melting. And this is looking down into the valley I've just come up from. Again, this view seems to indicate that a small belt of ice persisted for some time in this trough after the interglacial period of modern times commenced. And if we look onto Mt Townsend, you can see up on top there's a lot of pointy rocks. And I'm thinking that these rocks over here are also those pointy rocks. Rocks that have been shifted can often be traced back to their source by studying their shape and colour. The larger rocks would surely be erratics. Larger erratics in higher places like this have often fallen onto the glacier from above and then been carried along on the surface. We can see that the rocks continue sweeping down to the right here. Rocks scattered across the floor of a valley are often known as ground moraine. They are the residual rocks that were caught up in the ice when it melted. Again, Mt Townsend. This is Mt Townsend's most southern and therefore coldest face. It looks like a cirque has formed here, that being a bowl-shaped depression at the head of a glacier. It's more noticeable when viewed from a distance. Any moving ice would be heading down this way. A little further down the valley was another belt of rocks. Here's another area where rocks have collected. This could be another accumulation point from the retreating glacier as the ice withdraws in stages. Here's another example that indicates the source of the rocks. We can see signs of the mica deposits from up higher. The rocks have also had their sharp edges ground off. It wouldn't be unreasonable to think that ice came down from two directions here. One glacier coming down from the saddle next to the Abbott peaks, and the other from the cirque on Mt Townsend. Just below was the joining of the watersheds from these two valleys. And from here everything drops down into the Wilkinson Valley. Any ice extending down from Mt Townsend would have joined up with ice forming here in the Wilkinson Valley. Just before I drop down onto the valley floor, I'll just head over to this feature over here, more on the Abbott side of the valley. Here again we see the U-shaped valley, typically carved by glacial ice. It's hard to imagine how a block like this would have been left standing up. It could be some time off, but this one will get shifted in the next glacial period. More smoothed surfaces. The greatest concentration of ice would have been in this main valley. As we can see, all of the landforms have been smoothed off. Anything sharp is likely to be an erratic. This is the feature I wanted to point out. Here we go, and I'm pretty sure this could be classed as an arête, and they're formed when ice runs along either side of some rocks and it creates a sharp divide. We can see by the polished faces here that ice has been through this way. An arête is categorized as a sharp ridge between glacial valleys. They're often a much larger formation than this. There's Mount Kosciuszko up there. The shaping here suggests the path of a massive flow of ice along the shelf in the foreground. And this is the Cirque basin of the Wilkinson Valley. That's Mueller's Pass up above. All of the glaciers that came down from Mt Kosciuszko, Mt Townsend and the Abbott Range would have converged here. Just like the Blue Lake Basin, a depression would have been gouged into the earth from the incredible weight and pressure. But if a basin formed here, it must now be filled in by sediments. So there we go. Have a look at the glacial features on this side of Mt Townsend, leading down to the Wilkinson Valley. Excellent stuff. And it's actually quite hard to pinpoint what features come from which cold period. It's all sort of fairly jumbled up together, but it's good just to have a poke about and see what there is to see. So I guess I'll sign out here then. Adios.